Hi students, today we're going to talk about the mechanical vibration. Okay, for that I have created a small pendulum for my old piece of mirror. Okay, now if I start my pendulum from this point, we can see that it oscillates and eventually so this amplitude will decrease and it will stop here. Okay, now how can we obtain the equation of motion of such a pendulum? So that's one thing we're going to learn in this lecture. Okay, now let's assume this pendulum is operating in vacuum. That means it does not have any air or air resistance. So in that particular case, the motion of this pendulum will be somewhat equivalent to a spring attached to a mass and the motion of the spring mass system. Okay, so in that particular case, since there's no any air resistance, this vibration amplitude will have a constant amplitude, or it will oscillate between 2 points, and that will sort of like have a sinusoidal wave, okay, with a constant amplitude. And we can actually calculate this amplitude as well as its period and the frequency. We can do all sort of calculations once we know how to model the equation. Okay. Now, let's come back to reality and let's say now, look, I am operating in the real world with the air. Okay, now what happened is this air act as a resistant or as a damper. So it damp out this motion, which means the amplitude that it's oscillating or vibrating will decrease over the time. So it will be like have a large sinusoidal wave, but eventually the amplitude will be decreased. We call that act as a damping effect. Okay, so that motion, which means a pendulum operating in air with air resistance, is quite equivalent to a spring mass damper system. We have learned about it. We have learned how to get the equation of motion of a spring mass damper system. Okay, the spring, when we have a spring, it will generate an oscillatory motion, but once we have a damp attached to it, it will like damp out that oscillation. So that means the oscillation amplitude will be will get smaller and smaller and smaller over the time and come to, so in the case of a pendulum, the pendulum will eventually come to its stable equilibrium point, which is the downward position. Okay, now we're going to learn in detail about what are the different types of dampers we have. We can generally classify this damping as 3 different types: underdamp, critically damp, and overdamp. We're going to learn about them in detail during the class. Now, underdamp means yes, it does operate under the damping. That means the oscillation amplitude will eventually decrease and the system will come to its stable equilibrium point. Now, critically damped is a situation where this is a two-dimensional system which can be described by a second order differential equation, which is a linear with constant coefficients, which we know how to solve, and so which will have 2 different roots, and these roots, if the roots are equal, then we call it as critically damping. And the next one is overdamp. Okay, so underdamp to critical damp to overdamp happens when we have a stronger effect of damping. The overdamp has the strongest effect of damping, or the damping coefficient is large or comparatively high. So in case of critical damping and overdamping, it will not have oscillations. It will come to the equilibrium point, or it will have a minimal oscillation and come to the equilibrium point. Okay, so only in the underdamping case we'll have oscillations and then eventually come to the equilibrium point. Okay, so we will learn in detail about how to classify these three different types of dampings and how to talk about the frequency and the time period and the time lag in case of underdamping. Yes, that's what we mainly going to do in this lecture. See you in the lecture.